All right, part two. Picking up where we left off, we're talking about the gear called sonar was developed in the 1930s. It worked by bouncing sound waves off the seafloor. Sonar equipment on board received the waves and determined the seafloor's depth and features. At the time, a geologist from Princeton University named Harry Hess, we have a new person here that we're talking about, so let's highlight his name, was in charge of a military ship. Hess wanted to continue his scientific studies even while at war. Ship commanders usually only turned on sounding gear to navigate when docking. Hess, however, left his ship's gear on all of the time. What Hess discovered was a big surprise. The bottom of the sea was not as smooth as expected. In fact, it was full of canyons, trenches, and volcanoes. All right, we are going to highlight what he found out. By the 1950s, other scientists have found that a huge crack ran along the top of the mid-Atlantic ridge. We're going to highlight that sentence because it adds on to what Harry Hess learned. The discovery enabled Hess to understand what he had learned about the ocean floor of the Pacific. He now knew that the Earth's crust had been moving away on either side of oceanic ridges. And we're going to highlight those two sentences as well. The ridge ran down the Atlantic and Pacific Oceans. They were long and volcanically active. He published his theory in 1962. It came to be called the seafloor spreading, and we're going to highlight what it was called. In the early 1960s, samples were taken from deep in the ocean's floor and dated. They showed that the ocean floor was younger at the mid-Atlantic ridge and became older and older in either direction. This confirmed that the seafloor was truly spreading. And so we need to highlight what all of the evidence together proves. Unlike Wegener, Hess lived to see his major theory accepted. He helped to plan the U.S. space program. On August 25, 1969, he died of a heart attack. It was just a month after the Apollo 11 mission brought the first humans to the moon. Plate tectonics. By the 1970s, geologists had agreed to use the term plate tectonics. So now we're going to call seafloor spreading plate tectonics. They already knew that the continents move, but now they also have found evidence that so do whole plates of the Earth's crust. We need to highlight that we know that the continents moved, but it's not just the continents, it's the actual, all the plates move on the crust as well. A plate might include a continent or parts of a continent. Even portions of the Earth's crust now underwater can form plates. Wegener's idea of continental drift had taken a step further. Geologists today understand that the Earth's crust is broken up into 8 to 12 large plates and 20 or so smaller ones. So we're going to highlight how many large and small plates we have. These plates move in different directions and at different speeds. Their size don't match the land masses on top of them. For instance, the North American plate is much larger than the North American continent. The plate starts at the western coast of North America and extends into the middle of the Atlantic Ocean. Iceland is split down the middle. It belongs to two different plates. The continents have come together into one large mass and then split apart again more than once. Over the last 500 million years, this may have happened as many as 3 times. The force that moves the plates is thought to be convection currents in the Earth's mantle. We need to highlight what we think moves the plates. The mantle is the area below the Earth's crust, separating the crust from the Earth's core. In the short term, the mantle is solid. But over longer geologic time, the mantle does flow, though very slowly. And plates float on top of the mantle. Pockets of hot liquid magma in the mantle ooze up along the mountain ridge, deep under the water, forming volcanoes. All right, I'm running out of time again, so there's going to be another part to this video.